If you want to make custom electronics, you kinda need to be an expert at 3D modeling software, spend lots of time learning the advanced interface and tools, not to mention the circuit board software and all of its complex designing of schematics and PCB layouts, and somehow you need to make this all fit and work together. But what if there was a simple way to convert a PNG image into a PCB? And 3D modeling was as easy as adding or subtracting primitive shapes together in a non-destructive way. And all of this could be created in one program. This is the method I have discovered, and I can't wait to show you. But first, I want to thank this video's sponsor. I've honestly been using JLC even before they reached out to me. I've just always been happy with their speed, support team, the board quality, and they want you to know about their 6-layer PCB manufacturing. And why 6 layers? Well, sometimes you're routing a complex design on 2 or 4 layers. It leads to routing nightmares. But if you have 6 layers, you can have a dedicated ground and power plane, and an extra signal layer. Up to 50 by 50 millimeters for 5 boards starts at just $2. Up to 100 by 100 millimeters for 5 boards starts at $36. So if you want to try 6 layers, I'll provide a $30 coupon in the links below, and you're not going to be waiting long because they have a 48-hour quick turnaround to manufacture these 6-layer prototypes, and they have some pro features like free VIA in pads, and ENIG surface finish is a standard. So thank you again JLCPCB for sponsoring this video. If you are intimidated by 3D modeling programs, I highly recommend Tinkercad. It's free, simple to use, and is designed with 3D printing in mind. I recommend starting simple by editing the dimensions of a shape by dragging or entering values. And all objects can be a solid or a hole, and they will correctly join together when grouped. And those groups can always be opened, values edited, and then regrouped back together. And even a large group of shapes can be joined, cut, and have this repeated over and over while still being able to go back and edit. And I've used this process to create a few of my old projects, and Tinkercad has several pre-made adjustable models too. And I like how simple the tools are and easy to use, like rotating with the mouse outside the circle or inside to snap angles. And many of the shapes have adjustable properties. And you would be surprised with how easy it is to create most anything by using these simple tools. And then when you're ready, export as an STL, import into your slicer program, and then send to your 3D printer. Turn your ideas into helpful, functional items. Use a caliper to accurately measure your items. And it becomes very satisfying to use this process to design your own custom storage containers. And it's hard not to smile at the things that you make. And while I create my own PCB enclosure, I want to show you a challenge you might run into. You probably want a rechargeable battery, a power switch, a USB-C charger board, and a way to regulate that voltage. And these components need their own board on top of your actual board with its components. So I found a way to easily combine the charger and battery to make the design more compact. I found these 9-volt rechargeable batteries with many great features, 1300 milliamps, built-in USB-C charging, and best of all, built-in safety like overtemperature and short circuit protection. So here's my finished electronic enclosure, and I'll also want to create a box for my PCB and the front cover too. And it's really helpful to 3D print and test fit the pieces, make adjustments if needed. And I added this spacer to lock in the battery, and I can adjust its height for a taller enclosure. And thanks to the USB-C charging port, you never have to open it to change out the battery, but you could swap out the battery if you need an instant recharge. Tinkercad has a lot of built-in electronic components, and for anything you can't find, I recommend Grabcad. They're all free models that are usually saved as a step file, which Tinkercad can't import, but it's easy to find a free online browser converter that will save it as a STL. And it's so helpful to be able to move the parts around to see how they fit and how you want to arrange them. Now, this is important. I'm going to make the drill holes a solid red color, and then the board will be pure white. And this will make sense very soon. So the components will help you align the holes to where they should be, and from here you have 2 helpful options. Option 1, you can 3D print the components to see how the layout feels. Or option 2, you print the board with the holes and insert your own components. So I'll capture a screenshot to sketch out the trace routes. Alright, so let's see. My power will come into the switch, and then into the buck converter, and then out to the main ESP32. Alright, that's good. And then we'll do the same thing for the negative route. And I can connect the negative poles of the LED and speaker, and same for the 2 push buttons to the negative pole. That's all the power, so what's left to connect is the output pins to the components, and I have a finished layout I can test on a breadboard. Next step is to add the large pure black cylinders around the red ones, and we can use the sketch tool to draw the lines in the same way we sketched it out earlier. You can then end the drawing with the check mark, and I'll go ahead and set the width to 1 mm. And you can always go back to edit the points if needed. And you will now see the shape in 3D. Make it pure black and lower the height. I'll repeat this process for the rest of the lines. And you will see a faint ghost line that we want to remove by grouping all the black shapes together. And this is going to make sense very soon, but next let's add the pure green text to help us remember the polarity direction of our components. And the text cannot overlap the traces in this example, or it might cut the connection. And we now have a finished board completely designed inside Tinkercad. Let's rotate to the widest direction to screen capture a PNG image. And use any program you like to crop out the black outline and rotate it if needed. So the secret and magical tool that we're going to use to convert this PNG image into a PCB is called Image to PCB, properly named. It is a paid software, but it's able to separate the colors into traces, silkscreen text, and drill holes. And I found this very helpful, and I haven't seen anything else like it. So there's no complicated PCB CAD software needed, and you can always edit the image to update the design. So here's what I do. I import the image, I keep the aspect ratio, I enter my board dimensions. So you can see the program found all the black pixels that we can export as T for traces. All the green pixels are the silkscreen we're going to label S, and you can export the outline as O, and it must be square or rectangular. And I'm really impressed with how it understands drill holes. So it recognizes similar sizes and visually groups them by color. So the black holes I made just a little bit smaller than the red. And it will add more colors for more diameters. And it did its best to guess the diameter, but I will update with the values that I want. And I'll add a separate solder mask file with an offset of 0.5 millimeters. And JLC recommends changing the file extension so it imports correctly. So here you can see what to edit for each layer. And I'm using a Windows machine, so renaming is super easy by creating a batch file, which is just a text file with the BAT extension. So just click the batch file and boom, I automatically have the files correctly named. Now just add the files into a zip folder. We can now go into the JLCPCB website and upload it to see how it looks. I personally like the 3D view the best, so I can spin it around to view it from all angles. And I wouldn't worry about the pixelation caused by image to PCB. In my experience, this is impossible to detect after it's manufactured. I also like to hide the solder mask to make sure that there's no breaks in the traces. Looks good to me, so let's send it to be manufactured. So I want 10 boards, 1.6 millimeters thick. It costs a little bit more, but I want mine to be lead-free. So the current price is $35, so that's $3.50 per board. That's okay, but I can lower it by choosing the cheaper and slower shipping. So now it's only $1 per board, and ordering a larger quantity can lower that price per board even more. So JLCPCB does a great job showing the progress updates. I also highly recommend shopping around for components. This same ESP32C3 component I found for $7, for $3, and then finally for $1.30. And it's all the exact same component. Alright, this next part is not part of my tutorial, but I want to share with you how great a laser engraver is to carve the traces, drill the holes, cut out the board, and even clean the board so you can quickly make a working prototype. But this copper is not protected or safe for production quality, and laser engravers are expensive, but they are dropping in price, so I just wanted to quickly mention it as an option. But back to the main tutorial. And while I'm at it, I went ahead and sent off another board so I can test many different holes, lines, and text sizes. You can better see the drill grouping shown here. And that exact same batch file worked here too. And this time, I'm going to choose the more expensive shipping, just for my knowledge and for you to learn about too. And I don't want to pay this much, but I will for this video because I want to learn how fast it can arrive. Let's take a look at the shipping results. The components from AliExpress were ordered on this day, and some parts arrived here, and the rest arrived here. So overall, the parts took 8 to 12 days to arrive. Now let's look at the results from JLCPCB. The slow shipping arrived in exactly 2 weeks, or 14 days. And the more expensive shipping arrived in half that time, exactly 7 days. And of course, your results may vary, but these are my results. Let's take a look at how the boards turned out. The text, traces, and pads all turned out really nice and clean. And it's nice to see that these traces are well protected compared to my laser engraved prototype. And the test board is great to find the perfect hole size for any of my components. and the measurements were very close and accurate to the original 36 by 53 dimensions. When soldering, I tried to keep the temperature around 375 Celsius. That works better for the lead-free option I chose. And I try to heat both the pin and the pad at the same time for a good second, and then hold for a couple seconds with the melted solder for a strong bond. All that's left to do now is program my game, upload it, close it up to play and enjoy. And I have no words to describe the feeling of converting your idea into a tangible, functional device, so I highly recommend that you just give it a try. And of course, do your own research, learn, and design safe electronics. I hope this helped you in some way, or at least you were entertained or learned something new. And thank you for watching, and let's hang out again sometime, and see you next time.